All right, chemistry students, let's jump from the Bohr model into the quantum model now. Lesson 4.4 is the introduction to the quantum atomic model. In this lesson, we want you to be able to state the Heisenberg uncertainty principle, to recognize that light has characteristics of a particle, and to also recognize that electrons have characteristics of waves. This goes with text sections 6.1 and 6.2, and I'm not going to lie to you, quantum chemistry is weirdness. So we're going to get into the weirdness that is the electron and attempt to understand it, at least on a basic level, of how we conceptualize atoms now. So we're not going to include any post-video questions at the end of this, but there is kind of a summary section of things that we'd like you to remember from this lesson. So make sure you copy that down, and as well as any questions you might have about this lesson. And we will definitely discuss this when we next meet. So have fun.
So Max Planck in the 1900s, he was an important scientist who was doing some experiments. And the first one was the black body radiation experiment, and he could only explain it by if he viewed light as a particle. So in doing so, he put the first, experiment up there for quantum physics, actually, in which they went from one level of thinking to the next. So now we think, or he makes us think, that light would be a particle.
We already had numerous other experiments that showed that light acts as a wave. And it can be diffracted in a double slit experiment and show interference. So this is a diagram showing the famous double slit experiment. The lines running...
You're good to go.
Lines running this way would represent the wave crests, and you could think of some water waves heading this way.
Yeah.
And when they come to these two openings, light has a property called diffraction, where it spreads out as it passes through a narrow opening. And so if we have two narrow openings there, the light diffracts differently through each opening, and the net effect is you're going to see an interference pattern on this screen, where in some places the light waves add together and strengthen each other, and you get a bright spot, like here and here. And then in other places, the waves... The crest of one wave meets the trough of another one. They kind of cancel each other out. That's these dark spots.
Yeah.
This is called interference. So
you have constructive interference and destructive interference.
Right.
So the constructive gives you those nice white or bright spots, and the destructive interference gives you the dark spots, the spots where there's no more light.
So this was verified in many experiments. Mr. Hunter and I will demonstrate this for you. Light totally does this when it goes through two narrowly placed slits, and which is pretty powerful evidence that it acts like a wave.
Yeah, so this was the evidence they had before the black body radiation, and with the black body radiation, it made scientists stop and think and wonder how it can have both a property like a wave and a property like a particle, which made the light to be viewed as both.
You have to think of it as both at the same time. So basically we stop trying to fight about whether it's a wave or a particle, and we just say it's got aspects of both. It has what's called wave-particle duality. It is both a wave and a particle at the same time, depending on what experiment you're running.
Yeah, and if you're wondering what you should write down based on this picture right here, I think the biggest point would be kind of this interference pattern in the back. If you want to try to do the art of the interference there, that'd be great, but you should definitely know what this looks like right here. I'm pretty sure that comes up on some of our
like on the study
tests
island
or the study islands.
Yeah, absolutely. So the next major kind of advancement in how we think about matter and light came from a French scientist, Louis de Broglie, in 1924. And he was kind of thinking about electrons. And he thought, well, if we can think of light as both a wave and a particle, maybe we need to start to think of particles like electrons as having a wave-like nature. You know, if light, which we thought was a wave, really acts like a particle, maybe particles like electrons act like waves. And so this hypothesis actually allowed him to kind of go into the Bohr model and explain really nicely the reason why hydrogen atoms have these energy levels in the place they do, because those are the places where, when he set up to solve for the electron's wave function, the wave function is a perfect standing wave there.
Yeah.
And if you think of a standing wave, if you shake a
jump rope against a tree.
Up against a tree, and you get it so that the waves are a perfect standing wave where they're going forward and backward at the same. There's these nodes that don't go up and down, and then the other parts oscillate. We can demonstrate this for you as well, probably easier than
it is to
we can
explain
it.
So the thing that the experiment they used to test this is they basically took like an electron gun, and they took the same kind of double slits, and they fired these electrons at these slits. And what they noticed over a period of time, they started to get an interference pattern to build up, as you can see drawn off to the right there. This interference pattern, if they didn't know about or wanted to predict the wave-particle duality, they would have expected them just to have two lined up right here. You'd have electrons here, you have electrons here, but somehow these particles are interfering with each other, which is mind-boggling to
me. Very wave-like.
Yeah. So there's these like little, basically marbles that are, interfering with each other and causing these, dark spots and light spots, which to me is exceedingly crazy.
It's crazy.
But that's quantum chemistry, it's quantum physics. The quantum world is extremely odd, and we're going to watch Dr. Quantum in class, and he'll give us a pretty nice view on this as well.
So now we have the ability to look at things that we previously thought were just particles made of matter as having a wave aspect to them. When we look at light, which we thought was a wave, has a particle aspect, and it starts to kind of blur the lines. And like Mr. Hunter said, that's quantum
weirdness is the best way to put it. All right, on we go.
The real advances in our modern model of the atom came when scientists were trying to explain the energy level concept that Bohr had, and trying to actually figure out a way to map where the electrons that had different energies would be located around the atom, and then attempting to predict, if it's here now, where is its future location.
And what they were trying to study these with were using electrons. They were trying to use electrons to study electrons. And if you think about trying to study one marble with another marble, if you hit one marble against another marble, they're both gonna, fly away. So this is the same problem they were having with their electron studies. Every time they bombarded at something with an electron, one electron was knocking the other electron away, and this led
so
Heisenberg.
You might find out where it was, but now you've knocked it off course.
Yeah,
so you don't know
you know where it was at, but you have no idea how fast it was going, or vice versa. So Heisenberg, if you watch Breaking Bad, yes, Heisenberg, came up with the Heisenberg uncertainty principle, in which he said that the position, and it's not velocity, it's actually momentum, are something known as a conjugate pair. So the more you know about the one, the less you know about the other. So if I know the exact position of this thing, of this electron, I have no idea what its momentum is.
Its course is.
Or if I know the exact momentum of the electron, I have no idea where its position is. So these are known as conjugate pairs, and they come up quite a few times. It also has one with energy and time, and I think there's another one which I forget off the top of my head. But these pairs are things that are basically restrictive because of our measuring technique.
But in terms of trying to map the location of where these electrons would be, what Heisenberg's basically telling us is we cannot predict the exact position of an electron around an atom and know how fast it's going at the same time.
But here's a little cartoon for you that illustrates that.
So the couch potato, lazy, no good electron husband, how can you possibly know where I am at and how fast I'm going at the same time? That was his response to the wife saying, I'm leaving you. You are at a dead-end job and going nowhere fast.
So position and
he's saying you
speed.
can't know where I'm at and how fast I'm going at the same time.
Yeah. So that illustrates well the Heisenberg uncertainty principle. And for those of you who are Futurama geeks like myself, there was an episode in which there was horse races going on, and the horses finished in what they say is a quantum finish, and in the background you hear the professor screaming, "That's no fair, you change the outcome by measuring it." That is completely a quantum phenomenon. If you measure something in quantum chemistry or quantum physics, you do change it because you're modifying it. So I was the only person in the room who laughed, but hey, made me feel like a geek. All right, on to the next. All right, next is a scientist or a physicist by the name of Schrödinger. He developed equations based off of the previous oddities that he saw, and what his equation allowed us to do is to predict statistically using energy where these electrons should be found. So here's the best part about this slide. This big equation down here is something I had to calculate in grad school. It's a pain in the butt. The good news is you don't need to understand the equation and how to calculate it to understand the ramifications of the equation. Basically, it's allowing us to discover the energy or discover the position or discover whatever we want, and it all depends on this part up here. These are known as, I believe, operators, and whatever operator we choose will cause a different outcome to occur, and you can use this very powerfully for a lot of things, but the biggest thing we need to know about this equation here is it allows us to predict statistically what the wave functions look like, where the electron should statistically be found, or the area it should be found in.
The likely area around the atom
Yes.
to find an electron with a particular amount of energy.
So it's this equation here that leads us to our next atomic model. But the good news is we're not talking about that atomic model in this lesson. It'll be the next. So
and the really good news for you guys is you don't ever actually have to look at
do
this again in this course.
To do these, you have to do derivatives and all kinds of crazy math, which makes your head want to pop. Because this number right here, that little psi is what it's called, is actually another equation, which is crazy because you're taking this equation and you're multiplying it by these two variables, and then you're multiplying it by this and adding it to this equation, which is also a variable. It's mind-boggling. But anyway, notice one's position, one's energy. This gives us the position and the momentum. So that's all that matters. It's proving to us, as we know one, we can't know the other as much. So that's all we need to get out of this slide for now.
Okay.
So the question you should ask yourself is, there might not have been a lot of writing for you to do on these slides, but there are three very important things that Mr. Ferguson and I feel that you need to know. And the first one is the fact that light has both a wave and a particle nature to it, known as the de Broglie, or the Broglie duality. Thank you. And the second one, of course, is that electrons also have a wave and a particle nature.
And actually, the quantum physicists would tell us that everything that's made of matter.
Yes, technically we have a wave nature, but since we're so massive compared to an electron, our
wavelength is extremely huge.
Yeah. And then lastly, we should also know that the modern models of the atom don't attempt to have both the location and the momentum of the electron, because they can't do it. We will show you a cool little, video at some point showing how these electrons move about. They don't move like classical particles. They don't move in a straight line. They statistically move about and pop up in random locations. Kind of think of a gopher coming out of different gopher holes. It doesn't always come out of the same gopher hole. It can come out of a different gopher hole. So that's kind of
how
what
it goes from point A to point B.
We don't know.
That's a mystery.
But it just pops up in some other location at some certain speed with certain momentum, and we don't know any of that. So I hope this was enjoyable. If you're curious, look up some guy with the name of Dr. Quantum, and you can get a head start of us in class. But we are watching it in class. Otherwise, have a good night.
See ya.